Good morning, everyone. Thank you for joining for this distinguished webinar series in AI and cybersecurity at UND. Today's distinguished speaker is Dr. Sid Suryanarayanan. And he's the Chief and Principal Engineer at Eaton Research Labs. Today's title is focused on risk-informed hierarchical control of behind-the-meter distributed energy resources for grid services. Dr. Sid is the Chief Engineer at Eaton Research Labs, where he researches distributed energy resources and microgrids. He earned his Ph.D. in electrical engineering from Arizona State and spent 18 years in academia before joining Eaton in 2022. Dr. Sid, thank you so much for taking the time and effort for joining this webinar. We're grateful for your time and effort. The floor is yours. Now you should be able to share the screen.
All right. Thank you, Dr. Ranganathan. Give me just a second while I get this. All right. Nirup, can you confirm that my screen is visible?
Yep.
All right. Okay. Well, first off, thank you for inviting me to give this lecture. I'm thrilled to attend and address your audience. As the title says, it's on control of behind-the-meter distributed energy resources, and this is for providing grid services. And what we are going to look at today is how to access those behind-the-meter resources and bring them to provide a value proposition for the grid, for the utility. Okay. And with that, I'll get started. I don't know how the webinar is set up, meaning is it set up in such a way that I go through my slides and then take questions if there are any, or if there are questions that can be asked as and when. I'm fine with either.
Great. I think we'll let you complete your slides, and we'll also take a parallelly Q&A on the chat, so we can able to collect those questions, and then we can talk or discuss at the end of your presentation.
Okay, sounds good. All right, let's get started here. Okay, let me start by telling you a little bit about my employer. Eaton Corporation is an intelligent power management company, right? We are located in 175 countries. We have an annual sales of over 19 billion USD, and Eaton employs 85,000 employees. And as a global power management company, Eaton helps customers solve their greatest power challenges through industry-leading electrical, aerospace, e-mobility, and vehicle products and services. If you have been on LinkedIn, if you're on LinkedIn, you might have noticed that Eaton recently celebrated a milestone event of being listed on the New York Stock Exchange for 100 years. This is something that is claimed by only a handful of companies. Now, when it comes to corporate global research centers, Eaton Research Labs serves as Eaton's global business segments. Eaton Research Labs is the corporate arm of Eaton's global business segments, be it electrical or industrial, and for worldwide corporate locations. I am located in Golden, Colorado, where I'm actually co-located in the National Renewable Energy Lab. Right. In the U.S., we have teams located in Milwaukee, in the Detroit area, in Minneapolis, and in Denver Metro, where we are conducting research on power electronics, energy systems, additive manufacturing, materials sciences, cybersecurity, and renewable energy systems, right? And specifically in Golden, we are the only private industry or vendor located within NREL's ESIF building. We have a state-of-the-art lab inside ESIF where we conduct highly specialized research on topics related to DERMS. DERMS stands for DER, Distributed Energy Resources Management Systems. That includes anything from your standalone PV to microgrids, and that's my area of research. We work on grid intelligence. That could be advanced algorithms for wildfire prevention. How do you prevent a wildfire? You detect a high impedance fault really quickly and isolate it fast. Okay, and DC distribution systems. You want to look at what's going on in the world of electric vehicle system architecture, charging in infrastructures. Those are all part of the topics that we are trying to move the needle so that we are creating technologies that are relevant for tomorrow's grids. We are also located in, I have teams located in Prague, in Czechia. I also have teams located in Pune, India, where they provide resources and contribute to these topics. Okay. When it comes to the specific area of research under energy systems, in Golden, we are engaged in 3 of those intertwining topics, but there are 5 topics that are included in the energy systems theme within Eaton Research Labs. And our technological solutions straddle those 5 intertwining areas. Those are intelligent machines, their prognostics, health and monitoring, distributed energy resources and microgrid management systems, controllers, tools, development, anything from sales tools to management tools, controller tools. I talked to you about DC distribution and EVCI. EVCI stands for Electric Vehicle Charging Infrastructure, equipment integration and systems, grid connectivity, digitalization and cyber resilience, and advanced grid management. And as I said, these are intertwined topics. For example, your EV itself is a DER if it is capable of participating in vehicle to grid or vehicle to building modes of operation. This was I used, as Dr. Ranganathan mentioned in my bio, I spent nearly 2 decades in academia, and as an academic researcher, we probed vehicle to grid algorithms. Right? When I did that, that was usually sidetracked by Detroit, the automotive industry, as this is academic research. Who's ever going to let the utility or a homeowner access the battery on board a vehicle for charging a home, or for powering the loads in the home, right? You automatically would lose warranty on a battery. So Detroit would not approve of such actions. All that's in the past. Now, actually, you look at car manufacturers. Not only have they moved past the idea of making electric vehicles or increasing their options of providing electric vehicles in their fleet, but they're also considering V2X, V2G, X being replace X with anything, right? X can be G, where G stands for the grid, or B for a building, or H for a home, or V2V, meaning vehicle to vehicle. The simplest vehicle to vehicle for a for a internal combustion engine is when you jump a car in the whose battery is dead, right? That's a vehicle to vehicle. But in a in the world of electric vehicles, it's a different deal. Detroit is thinking about those, right? Not too long ago, there was a Super Bowl ad where Ford put out a advertisement where Ford Lightning was powering a home. I was floored. Anyway, such things are very important. And if you look at what's going on in the world of electricity, energy transition is the key word. The industry is focused on that phrase. Energy transition is the concerted change from what we have today towards a more sustainable and a lower or a no carbon future, so that we can limit the human impacts of climate change. This particular transition is driven by some mega trends, right? In electrification, where we are, as I said, we are looking to move away from gasoline-powered automobiles and catering to the projected demand or increase in demand for energy from the residential and commercial building stocks. And this is the mega trend over the long period, long time horizon, 2050. And a significant portion of that demand is expected to be met with renewable energy sources, majority of which have not yet been installed. Meanwhile, the power grid is facing a need for energy resilience, be it from more frequent and severe hurricanes or from the need to support and stabilize the grid when it is powered with more intermittent power plants. Probably you're all familiar with the eponymous duck curve. It was only last week when CALA, so California Independent System Operator, reported a net load meaning the difference between the actual load and the renewables supplying the grid, was near 0 megawatts. That's fantastic news, right? As of this month, April 2023, nearly 13% of California ISO's load was supported by peak battery discharge. Compare this to November 2021, when that was just 15%. That was just 1/3. What this means is the need for storage is profound as the nation, as the United States, embarks on installing renewables to decarbonize. And this is not just the United States, this is a global phenomenon. And perhaps the biggest enabler, in my opinion, is the government stimulus, boosting the infrastructure and paving a path for this energy transition to occur in the near term. Okay. All right. So what does this mean for behind the meter end user side? What do these trends mean for the end user side? If you look at the residential sector, this means we expect nearly 21 million residential electric vehicles, 15 gigawatts of new solar and storage systems, and PV panels on the rooftop of 1 in every 7 homes in the United States. That's nearly 7 million single-family homes. Okay, collectively, these devices are part of flexible loads, along with your traditional electric water heaters and central AC units that can now potentially be used in load management and grid services. Why do they matter? Remember, we were talking about the duck curve, the need for flexibility on the load side, the 13% peak battery discharge. That's all that flexibility is needed because the power grid is a beautiful balance in a 16 millisecond time step, right? That's the metronome for this dance. If your demand is not equal to the supply, then things can go awry. Okay, a report from Wood Mackenzie from just a few years ago predicts that in 2 years, the cumulative potential of the global residential segment's load for participation in flexible grid services and load management could be as high as 50 gigawatts. And that market for residential mixed assets could go over $1 billion by 2030. And that's the global market, right? Meaning we're talking huge numbers. We're not talking peanuts, right? Viewed from the perspective of home occupants, the individual home occupant, bringing on the additional resources should result in about $200 to $250 annual savings per connected home. Another way of saying it is a utility with about 10,000 units deployed on its system could save anywhere between 2 million to 2.5 million through grid services. Okay, those are all big numbers. So the potential is identified. Now, how do we achieve the technologies to unlock that potential? So for that purpose, we at Eaton Research Labs, we partnered with NREL, EPRI, Pecan Street, and Delaware Electric Cooperative, and through a contract from the United States DOE's Solar Energy Technologies Office, SETO, conducted research for developing and field validating a first of its kind TRL6 control technology to enable optimal provision of high value grid services from these behind the meter solar PV and any other synergistic DERs, meaning distributed energy resources. That is what I'm going to talk about in the next few slides. Okay, now there are major technology challenges in this topic. Okay. And I've only identified the 3 main ones that we want to address, that I'm going to address in this talk. And I'm going to keep it at a very high level because I have 40 minutes and I'm trying to condense the work of a large team over a period of 2.5 years. And I don't want to overwhelm the audience with too many details. So let's keep it at a high level. And at the same time, I'm also restricted wisely by my company to not reveal intellectual property. Okay, so high level discussions. 3 major technology challenges. First off, I'm the grid operator. If I am the grid operator, in how do I know what is available? Okay, what is the visibility of the DERs that are behind the meter that I can access and use in a grid service? If I am the utility and I own and operate a DER, then there's no problems. But now I have to access behind the meter, get behind the meter, get inside the home of a end user and access that. For that, I need visibility and control. Huge problem, okay? Second, how do I communicate and control those behind the meter DERs? Third, if I do it, what does the end user get in return? Most importantly, how does the end user do this without losing creature comfort? Meaning, are they going to sit there in a very uncomfortable situation, while they have just offered their DER for participating in grid service? No. So quality of service is an absolute firm constraint. The goal is to be able to access and piggyback on whatever advanced metering infrastructure technology that is available and working today. And why is that important? Because just 10, 13 years ago now, there was a large stimulus package that was released during the last economic recession, where the smart grid was rolled out, the smart metering infrastructure was rolled out, and the AMI infrastructure was, the advanced metering infrastructure was built from scratch in this country, right? So every 15 years, you can't come in and say, "Oh, I want to redo this multi-billion-dollar infrastructure." No, we got to be conscious of what is out there, and we should be able to piggyback on an expensive infrastructure build like that. But we should be able to develop unique architectures, algorithms. We want to come up with prototypical technologies that will allow us to unlock the potential of these behind the meter DERs so that we can use them for widespread grid services. Keyword I'm going to mention is reliably. How can we rely on them with confidence? So here's what we have. Here we see an architecture of how grid services, such as limiting loads during peak hours, are requested and procured from the residential segment. Okay, on this side, I don't know if you're able to see my laser pointer here. I can see it on my screen, so I'm going to assume that you can too. Okay, the current solution that we have out there, this is called demand response, is what you see on the left side, okay? And that's shown in blue. What happens is a request for peak shaving or demand response at, say, 6 p.m. to 8 p.m. for a day is generated by the utility operator at 2 p.m. that day. Now, that message is communicated through the utility DRMS. DRMS stands for Demand Response Management System, directly to these devices called load control relays to turn off electric water heaters or cycle AC loads at residences. And that is communicated through a mesh network like the radio frequency network, okay? The current solution is effective because it provides a one-size-fits-all capacity-based demand response. However, it has limitations. The major limitation is the comfort of the residential DER owner is not taken into consideration. In this case, the DER is the central AC unit or your electric water heater. Now, when the comfort of the residential DER owner is not taken into consideration with those two devices, think of cold showers or a hot home. Or you're in, many of you in the audience today are in Grand Forks, okay? So think late October, there is a demand response and your electric water heater is called in for a demand response event. And you just finished a long run in your basement treadmill, and you're looking forward to a nice hot shower, and you're not going to get that. That's what it means. On the other end of the on an example with the other type of the DER, I used to spend quite a bit of time, about 5 years of my life I spent in Phoenix, Arizona. That part of the country has 4 terrible months during summer. Okay, you don't want to give up your air conditioning during those months. Okay. The other limitation in the current method is the assets that are used in the current demand response has no, the current demand response methods are not applicable to other kinds of DERs. Let's say I have an electric vehicle today. Let's say I have a solar PV on my roof. This method does not allow a accessibility, controllability, communication capability to bring those assets, to involve them in flexibility. Now, why is it important to bring them? If you can bring them into this, you may actually be able to avoid that cold shower in Grand Forks in late October, or avoid that hot AC situation or a hot home in Phoenix in late August, because you may be able to manage these DERs as a whole. And that is the thesis of our solution here. Okay, let me see if I can advance to our proposed solution. In our proposed solution under the SETO contract, we have overcome those limitations by developing forecasting, learning, and optimization control algorithms for the residences and the utility DRMS. Now, I really have to give a shout out to one of your alumni, Dr. Arun Sukumaran Nair, who came out of Dr. Ranganathan's program. He has been involved in this project very deeply and has been developing all those fun algorithms. Okay, I don't know if he's in the audience today. If he is, then he has to take credit. Now, take the same example of the request for peak shaving or DR, same example, 6 to 8 p.m. Utility is asking at 2 p.m. to do this. By introducing intelligence, not at the LCR, but at the meter. Now, if you are able to put intelligence at the same meter, the smart meter, and customize those requests such that your availability of DERs is taken into consideration, then you are able to optimize the availability and provide an optimized commitment without violating the end user comfort settings. Then you have provided a better than state-of-the-art solution. The controllability of DERs and not just the traditional loads can perform peak shaving or valley filling, and that can flatten the load curve. This proposed solution has a greater chance of providing the collectively requested DR service. That's the thesis, okay? What you see here is the proposed solution. That's what we pitched to SETO, Solar Energy Technologies Office. What you see here are some of the enabling technologies. The first one is the architecture and algorithms. Look at home number 1 on the far left. There is an edge control or an edge controller. In that controller, an optimization routine runs or minimizes the electricity cost while maintaining quality of services. Quality of services means don't give me a cold shower, or don't keep my home hot, or any such user preferences. This is done by forecasting uncontrolled loads and scheduling controllable loads. A machine learning algorithm disaggregates the net load on the premises into individual appliances loads. Okay. In case there is a demand response, which I'll call a grid event, in case there is a grid event mode, the premise controller or the edge controller now manages its demand response, or I'm sorry, manages its DERs to ensure that your net premises loads do not exceed a certain threshold, a power threshold. Now, this controller on the edge of the home, or the edge controller, will communicate to a central controller. The central controller is located at the utility or the utility AMI head end, right? And it communicates with that. The central controller actually has more information. It sends weather and the grid event information, and that is all stored in databases for forecasting and calibration. It's important to consider both the grid event mode and or the so-called idle mode, right? Because grid event modes occur less frequently than the idle mode. The grid event occurs, say, 2 or 3 times a month. But you have the DERs the rest of the time. So any technology that you provide, the presence of the this technology should maximize the value for the end user. So what we've done is develop this technology in such a way that whenever there is a grid event mode, it maximizes the capabilities for the utility while providing a value proposition for the end user. And at other times, it maximizes the utility for the end user without considering the utility requests by maintaining the utility constraints. Now, this is a talk that is supposed to relate to artificial intelligence or cybersecurity. I am clearly not going to talk about cybersecurity because this project does not address cybersecurity. However, we have a lot of machine learning in this particular project. Unfortunately, because of time and because of the depth of those, I'm not able to go into the details. However, the presence of the machine learning algorithms in this particular technology is indicated in the red circles in this figure, right? Those are the ML algorithms. Anything that we are using for predicting the DER flexibility through forecasting, or anything that we are doing to disaggregate the load and predict the or the individual appliance information, rely on machine learning algorithms. Now, notice the figure in the middle. This is where we piggyback on the existing AMI, the RF mesh. Through the utility demand response management system, we communicate with existing load control relays. This is simply done to minimize any retrofits that are needed to implement the solution if it goes into a product, if it is productized. On the far right is the central controller or the utility level controller. This is an orchestrator that takes care of the grid event needs and resources, provides day-ahead information, engages in negotiations with the edge controller for any forecasted grid event. Notice, I said forecasted, so there is some machine learning on forecasting available here as well. No? Given that we do not have more than 40 minutes, I will not delve deeper into the details of this. However, if there is anybody in the audience that is interested in the details, I encourage you to look our publications and presentations up on IEEE Explore. Okay. Now, having established the architecture and the individual algorithms, the flow of information, and the overall system and data needs for this particular solution, we then proceeded to integrate all this in a simulation environment and validate it on the scale of technology readiness level, TRL. To validate it in simulation is at TRL 3. Okay, so put it all together and see if the thing works in simulations. Now, we don't want to build anything if it fails there, right? So as briefly mentioned in the previous slide, we have two use cases, an idle case and a grid event case. Or in this case, I've changed the name to grid services. I should have been consistent. An idle case is where the edge controller manages the DERs located in the premises without the need for a central controller. It just uses available information on on utility tariffs, such as time of use, and supports economic operations for that particular premises, except during grid service events or grid events. That is the second use case, or the grid event case, right? Then there is the interaction between the central controller or the utility controller and the edge controller. There is coordination, and there is a day ahead system peak prediction that uses forecasting algorithms, and then there is a 4-hour ahead system peak prediction adjustment if that is needed. In this case, I think our team used the coincident peak pricing or peak information from the PJM database along with the TOU. But no matter what, no matter which use case, the quality of service at the customer premises must be maintained. Okay, remember, no cold showers or hot homes. When we did this, our simulations compared to the state of the art yielded a 12% improvement in peak demand during the grid event. What does that mean for the utility? It means that the utility can actually avoid potential rolling blackouts if they are able to cut back on 12% of their peak demand. Okay, from the energy savings for the utility, it is about 2.5 to 5%. From the point of view of the utility, energy savings is not as important as it is to shave the peak. From the point of view of the DER owner, the end user, they can see anywhere from 12.5 to 20% cost savings. Now that is important. So it looks like a win-win situation for both ends of this. Okay. Okay, simulations say we are good. Now let's go and build a prototype technology. The enabling prototype technology is the meter controller, right? That we developed within Eaton Corporation. The meter controller approach allows revenue grade smart meter. Go take a revenue grade meter with advanced metering AMI channels and introduce those algorithms that were developed with the adapter, right? Many others are looking at adding collars. This is a prototype. So all those algorithms are mounted here, and that goes there. Now you have this meter controller follow, and this now talks to the, remember in one of those figures in the past, the meter never talked to the device. In the current solution, the meter is just for revenue purposes. For DR, the AMI was used for the RF network was controlling the LCR, which was controlling the existing traditional assets. Now, because of how we have set it up, this meter can talk to the LCR. LCR being the load control relay. Not only that, which means it can now control the traditional resources inside the home. And it can also talk to the head end, AMI head end on the north side. We have also introduced an IEEE 2030.5 gateway, which means we have future-proofed this technology. So it is ready for talking to electric vehicles, PVs, and battery energy storage systems, which we have in our setup. Okay, so this is what you're seeing here is TRL4, Technology Readiness Level 4. This meter was put through a lot of testing, unit testing, and it successfully passed all those tests. The next step is to conduct end-to-end validation using hardware in the loop. And this is what we are conducting at National Renewable Energy Lab, because we have we have a lab inside NREL, and we have a presence there. We are able to access and use some of the facilities there. So in this quarter, in 2023, we are fully de-risking this technology solution through this approach, where we are putting a wide range of what-if scenarios and testing this this solution. We have a PV simulator, we have electric vehicles, we have battery energy storage, we have our meter controllers installed, we have a utility grid service entry in that lab, we have our local gateways. Remember I told you that this local RF talks to the head end. Inside it talks to the whereas this talking to the LCR, electric water heater, and the AC. Plus, it is also talking to the individual DERs through the 2030.5. Plus, there are some uncontrollable house loads like dishwashers and laundry loads. Okay. So this is happening. Why is this important? Because we are able to do a whole lot of what-if scenarios that we will not be able to do in the field. But parallelly, we are also engaged in field demonstration in a partner utilities network, that's Delaware Electric Cooperative. What that does is it allows us to generate field data, which we will bring back to Golden. And our team will then use that field data to further train, test, and validate our machine learning algorithms so that the solution becomes that much more specific for the geographical location and the topographical network on which we are going to deploy. Now, if you're planning to attend the IEEE PES General Meeting in Orlando in July, we have a paper where we intend to make a deeper, more detailed presentation involving mathematics and other aspects. So I invite you to that session, okay? With that, I believe I've come to the end of my presentation. So thank you for your attention, and I will pause there.
Thank you so much, Dr. Sid, for presenting what's going on, what initiative that Eaton is doing in DER. So it was good to know all these reminders and facts and numbers in terms of the growing DER combination. So we'll wait to collect questions. Nirup, as you get questions, please let me know. And I see that other faculty from other universities also participating. Please let me know if they want to speak. We can even put them as a panelist to discuss, and so while we wait for the question, maybe I should start with this. And in terms of, how do you have any communication with DER owners, the third-party DER owners who are actually, of course, they are. I'm just curious to see how Eaton is handling behind the meter data by accommodating there are invisible services that are happening there, right? So I'm just curious to see how do you bring that into your AMI interface, because
that's a interesting question. At this point, we are so I have to explain who we are and what we do, right? We Eaton Research Labs is a technology solution developer, and we are not a product maker. We have an entire set of businesses and divisions that do it. So we engage with them to interact with our customers. So from a research point of view, we move happily up to TRL 5, cautiously up to TRL 6, and then leave it to the businesses to move it further into up to the TRL 9s, CRL, commercial readiness level, manufacturing readiness level. That's it. In this particular project, it's the goal is to get it up to TRL 6 along with our partners. For now, the customer, the behind the meter customer engagement is through our partner on the project, and that is through Delaware Electric Cooperative, and they are doing the customer engagement. I'm sorry that may seem like a non-answer, but that's the honest answer.
Great. I think you get me some. And you mentioned about working with NREL, right? NREL has released a DOE white paper on fast DERMS, right? Federated DERMS framework. I'm just curious to see whether is Eaton is relying on that type of framework while because when you talk about edge-based analysis, bringing machine learning there, I'm just curious if you can able to shed more light in terms of how as now, I think it's great that I see this effort, what you guys are doing in terms of this at the bringing this research component to the meter level. But I'm just curious to see when we talk about scalability for edge nodes, what type of efforts that on the research perspective that Eaton is coordinating with NREL.
I'm not sure I fully understand the question, Dr. Ranganathan. Could you? I think I lost you there a little bit. Could you explain the question again?
So I'm just curious to see whether have you had a chance to look at the NREL's fast DERMS framework?
No, I have not looked into the details of the fast DERMS particularly. No, okay. I should make a note and look at that. Yeah, thanks for pointing me to that. Yeah.
Okay, because we are actually working with them on this upcoming project. So anyway, Nirup, do you have any questions? Do you see? Does anybody have raised questions?
Yes, there's one in the chat from Dr. Kim. So his question is, I'm wondering about the scalability of the framework. How many homes can be controlled by the utility?
Good question. The scalability is this solution is highly scalable because you're only limited by the bandwidth of the radio frequency network or the particular network on which your AMI interactions are going to occur.
This 12% reduction in peak demand that you talked about for addressing how utilities is going to do this rolling blackout thing. I'm just curious to see again in terms of the numbers in the simulation or in the field demonstration. Could you talk about again the number of DERs involved, or what is that?
No, that the 12% comes to us from the simulation results of a typical simulation. Like I said, we'll be able to provide some more details on the simulation information. Actually, that is available in IEEE Explore already, but we'll be able to provide a little bit more details in the upcoming general meeting. However, the avoiding potential outages is more a conjecture. It's not a direct result of that. It's a meaning, okay, if you're a utility and you're able to gain that extra peak shaving, think of yourself in a situation as a utility distribution system operator that needs that particular amount of flexibility that you're unable to get from somewhere else. The only way to keep the system going at that point is to schedule your loads off the system. But by getting this 12% in, you are able to roll through that. That's the conjecture.
Let's see, I see some more questions popping up. This is from Dr. Tasik, came from Texas A&M Kingsville. Third-party DER aggregator is considered as a solution for the BTM DER control. Does Eaton plan to provide the solution as well?
So I acknowledge the first part of the question. Yes, third-party DER aggregator is certainly it's the go-to solution right now in the field, right? In the market. The second part, does Eaton plan to provide that solution? Is Dr. Kim's question related to, is Dr. Kim asking me if Eaton has plans to start a DER aggregator business?
That's what the question says. Yes, does Eaton plan to provide the solution as well, right? So I'm assuming that's the direction.
The DER aggregator solution. I am not in a position to opine about that. However, what I can tell you is we, as like I said, we are the research arm. We do not make. I do not, and I'm not in a position to make decisions. Let alone, I'm not in a position to make opinions on that. Yeah, but we. That said, on several of our projects, we work with partners who are aggregators. I'm sure you're familiar with many aggregators, like like NLX is one example that comes to mind. Yeah.
Great. Any other questions, Nirup? Do you see on the Q&A or the chat?
No, I cannot see. I think we're clear for now.
Okay. Very good. Thank you, Dr. Sid, for your time. I think, it's always this very insightful, nice to connect with you again through this webinar. So, and we will make the recording available, and as a token of your time and appreciation, I think we will send you a plaque from UND and a certificate signed by the dean. And thank you again for your time and effort for this presentation. And if you can share the copy of the slides, if it's okay, then we can also make it available on our website, so the audience can also use it.
Okay, thank you again for the invitation and for the questions. I enjoyed making this presentation. Dr. Ranganathan, I'll have to ask that about the slides, sharing the slides, I'll have to ask, and I'll get back to you and Nirup on that very soon.
Yeah, it's okay. It's optional. You just let us know.
No, whatever I've presented is public domain information, but I still have to get permission to share that.
Great. Thank you.
Okay. Thank you again. Goodbye.